that what are the different types of the shell we can have. So we find that this is the orbit and the orbitals. What is the orbit? Orbit is 1. Orbitals 1s. 2, 2s, 2p. 3, 3s, 3p, 3d. 4, 4s, 4p, 4d, 4s. 5, then 5s, 5p, 5d, 5f. Actually, in 5, we are supposed to have the G also. I told you the other orbitals like G, H, I, J, K, L, these are not there. So these are the orbits. And we always feel the energy of them is 1s is less than 2s, then 2p, then 3s, 3p, 3d, 4s, 4p, 4d, 4f, then 5s, 5p, 5d, 5f, then 6s, 6p, 6d, then 7s, 7p, like this. Okay, it's like this. So this is the normal. This is our usual knowledge that we have gathered, that energy is like this. But we find sometimes the energies, whatever we feel, this is not the true one. Okay, the energies are found to be different. All right. So now I'll teach you one theory by which you can find out the energy of the all the orbitals. Okay, please give me 1 minute time. I'm doing something. Okay. So how to calculate the energy? Energy of the orbitals. तो बोर्डটা মুছতে গেলে না মানে তো রাগ উঠে আর কি কিছুতেই যায় না কি করতাম আমি বোর্ডটা Now there is a rule called n plus L rule. Okay. To determine the energy of the orbitals. n plus L rule or Bohr-Baris rule is followed. There are two rules are there. One, the orbital with lower n plus L value has lower n. This n is principal quantum number and L is angular momentum quantum number. Okay. So let us go for it. How to calculate? So for example, suppose I have taken here 4s. So what is this n value? N value is 4. This is 4. And what is L value? You know, S stands for 0. So n plus L is equal to 4 plus 0 is equal to 4. All right. And let us go for 3D. 3D. So in this case, n is equal to 3. And what is the value of L? See, L, when L is equal to 0, it is S. When it is equal to 1, when it is equal to 1, it is P. And when L is equal to 2, it is D. So here, n plus L is equal to 3 plus 2 is equal to 5. Just now I have written that 3D 4s has higher energy than 3D. I have written, no? See here, I have just now I have written 1s, 2s, 2p, then 3s, 3p. I have written like this. And after that, I have written 4s. But what did you find actually? Actually, you have found the value of energy value of 4s is less than 3d. So that I'll tell you why I'm calculating, because in whenever we feel electrons are filled from lower energy level to the higher energy level. Now, same rule says, if if two orbitals have same n plus L value, the orbital which has lower n value will have lower energy. So let us assume that n plus L is equal to 4. So with this, what are the orbitals we can write? See here, I can write here 4s. See, 4 plus 0 is 4. And I can write here 3p. So it is 3, p is equal to 1. So here I can write now it is 4 plus x, so 4 plus 0 is equal to 4, and here it is 3 plus 1 is equal to 4. So which is having both the orbitals have the same energy values. Sorry, have their same n plus L value. So in that case, which one is having lower energy? This is having lower energy because what does it say? If the two orbitals have same n plus L value, then the orbital which has lower n value will have lower energy. So here the value of n is equal to 3, here the value of n is equal to 4. So this one is going to have lower energy. Write down. যাই হোক গেছে তো গেছি, তারও একটু ভালো লাগবে।
Done, sir.
Okay, wait just a minute. Let me put some ink in my pen. So now we are going for writing of electronic configuration. Okay, writing of electronic configuration. Writing electronic configuration of atoms. Okay, the following rules are followed while writing electronic configuration of atoms. First one is called AUF BAU, Aufbau. This is German word. Okay. Aufbau principle. Now what does it say? The principle states that states that electrons are added one by one into various orbitals in order of their increasing energy. See, if it is a step, I have to climb. Okay, so first we'll put our feet here, then here, then here, then here, then we'll go up. So similarly also, when you go for filling of the electrons, we'll fill it up on the basis of their energy. And I already shown you how the energy is being calculated by N plus L or Bohr-Barry rule. Finished?
Yes, sir.
Yes, sir.
Now I'll draw something, and this is going to help you in writing the electronic configuration, because why? When you fill up the electron, it is not possible that you will calculate the energy of these orbitals by using N plus L rule. So I'm going to write it. I draw some circle. Huh? Maybe that in some of the schools you have already drawn it, especially those who have gone for ISC, their classes have started long time back. So they might have already done it. One or two students are there from ICSC. I think one is there, Eileen, I think it's for ICSC. See, now by this your life becomes so easy. This is being arranged by following N plus L. Okay, so I'll show you. See, all these arrow means what? This will come one after another. Just now I showed you that 3p energy level, N plus L value of 3p and 4s is same, but energy wise 3p is less than 4s. See, now So on this basis only you are going to put electron. Means you will first put electron here, then it will go to 2s, then 2p, after 2p 3s, after 3s is 3p, after 3p is 4s, after 4s see we are not going to 4p, we are going to 3d, after 3d is 4p, after 4p is 5s. So after 4p you do not go to 4d and 4f, 4p 5s, after 5s is 4d, after 4d we are not going to 4f, 5p, after then 6s, after 6s it goes to 4f. So this is the order by which you have to fill up. So please draw it. Electronic configuration is not at all difficult.
Done, sir.
Okay. So now we'll write another principle. The second principle is called Polish exclusion. principle. So what is that? It said no two electrons of an atom will have identical all four quantum numbers. Means simple language that you will not find any second electron is having the same number of quantum numbers as the previous one it had. All of them are they are going to differ. They may not differ in all four, but minimum also they will differ by one. That is, you will not find two electrons with same number of quantum numbers, all four quantum numbers. Okay. So we'll say no two electrons in an atom will have all four quantum numbers same. It is, they will not have same. What are the four quantum numbers? Principal quantum number, angular momentum quantum number, magnetic quantum number, and spin quantum number. Assume three of them are same, then is going to differ in the fourth. What is the fourth? Spin quantum numbers. That is, if one moves clockwise, other will be moving anti-clockwise. Okay. Hmm? So let me tell. See here. Try to understand. If you wish, you can write, or you need not write. See, S or say it is 1s. Okay. But S will be small. 1s. So what is this quantum number here? N is equal to 1. Both of them, suppose there are two electrons are there. I'll write now here 1 as it is two electrons are there. So N is equal to 1. Both of them have the same principal quantum. Then L. L is equal to what? L is also here will be same. What is the value of L here? We know the value of L for S is equal to 0. So both of them will have 0 angular momentum quantum. Then ML. We know for each value of L, you are going to have twice L plus one value, starting from plus L to minus L through 0. I have told you for S orbital, the ML value is only 0 because it moves from minus to plus. Okay? 0. So all three of them are same for both the electron. What does the Polish exclusion principle says? No, that cannot be. All four cannot be same. See there, one of them will have plus half spin quantum number, okay, and the other will have minus half spin quantum. So it is very important for you to understand. That is, in an orbital, you cannot have more than two electrons because the moment you put the third one, it will be either plus half or minus half. Okay. So what we can write now here? Therefore, all suborbitals means what? Orbital is SPDF. Suborbital is what? Suborbital is S, PX, PY, pz, dxy, dyz, dzx, dx square minus y square, and I'm not going for f, and dz square can accommodate only two electrons, one with plus half and other with minus half. One with plus half and other with minus half. So this is most interesting. Okay. So I'll write down. See, S can have two. See, Px can have two. Py can have two. And Pz can have. So what is the total here? Total is 2. Here, total is 6. So p orbital can have maximum 6 electrons. P orbital mind. How we have calculated? We have calculated from their suborbitals. See here now. dxy will have 2. dyz will have 2. dzx will have 2. dx square minus y square will have 2. dz square will have how many? 2. So total is what? Total is 10. Similarly, F will have, F has 7 suborbitals. What is the total number? Total number is 14. So that written.
No, sir.
Right. If you understand this one, then life is become very easy.
Done, sir.
Okay. Now I'll calculate now what is the total number of electron you have in one orbit. See, now you already know that first shell has 2 electrons, second orbit or shell has 8 electrons, third has 18 electrons. Now I'll do it for you. Okay, so these are not mystery. You don't have to buy heart. See, first orbit. Okay, earlier you in lower class you knew it as K shell. Okay, first orbit. What you have? 1. What is the total number of electrons? Just now you have calculated. Huh? Maximum number of electrons. So S has the maximum capacity of what? 2. You know, first shell has 2. Second orbit. Second orbit is equal to what? N is equal to 1 and N is equal to 2. What you have here? 1s, that's 1. 2s, 2. So what you are going to have? S will have 2 electrons, and just now you have seen p orbital will contain how many electrons? 2 each in px, py, and pz maximum. 6. Total is how much? Total is 8. N is equal to 3. Third orbit. Third orbit has what? 3s, 3p, 3d. So now you know it has only one orbital, it has 3, and it has 5. So maximum is 2, p is 6, and d is 10. How much it comes? 18. See, this is called theoretical calculation. Nobody has seen the orbit, but what is their calculation is so amazing. Okay, now I'm to tell you. If they ask you that what is the maximum number of electrons present in third orbit with similar spin? See, half of them will have plus half and half of them will have minus half. See here, out of 8, you see, out of 2, 1 will be plus half, other will be minus half. Out of 6, 3 will be plus half, 3 will be minus half. Out of 10, 5 will be plus half and 5 will be minus half. So, what is the maximum number of electrons having the similar spin? Out of 18, 9 will be having plus half and 9 will be having minus half. Why? Because in this case, the value of N, value of L, value of ML are same. So it is going to differ only in the spin quantum number. Half will be having clockwise spin and half will be having anti-clockwise spin. For clockwise spin, we use the symbol plus half, and for anti-clockwise symbol, we put the symbol as minus half. Okay. Now we'll go for the third one. Third one is called Hund's rule, or someone say Hund's also. Hund's rule of maximum multiplicity. Hund's rule of maximum multiplicity. Okay. Right. While filling the electrons in orbitals having same energy. Electrons with similar spin will go to each of the suborbitals. See here, this one you'll have little difficulty. Say I have written here p orbital, and suppose it is having 3 electrons. So we have here, this is px, this is py, and this is pz. All 3 of them have the same energy. If you go by following Hund's rule, I'm supposed to put 2 here, 2 here, because it can accommodate maximum 2, and out of the 3, 2 will be here, and the third one will be here. But Hund's rule says no, it is not like this. It will be like this. First, the similar spin will go. So it will be 1 here, 1 here, 1. Now, if it is say P5, so this is Px, this is Py, this is Pz. So it will not be 2, 2, 1. It will be 1 here, 1 here, 1 here. Then after that, what you have? You have 2 more. Then it will be this and so electron with a similar spin will first build up. So this, and this have the same spin. It may be plus up or minus up, and this and this they have opposite spin. So this is called maximum multiplicity. Okay. Same will be case with the d orbitals.
Done, sir.
Okay. So now we'll write some electronic configuration. Okay. So before writing the electronic configuration, all these circles that I have drawn, please again draw in your copy. Please draw it. This one you have drawn or no? 1s, 2s, then 3s, 3p, then 4s, 4p, 4d, 4, 5s, 5p, 5d, 5s, 6s, 6p, 6d, 7s, 7. Please draw. Then it will be easy for you to write the electron. This. Okay, now you know this will be like this. This is the one. And one more thing, what you are supposed to remember: S2, P6, D10, and F4. You can go to the next orbit only when you have filled up the previous orbit completely filled up. Finished?
Yes, sir.
Finished, no?
Yes,
Okay.
sir.
Then we will write for electronic configuration. Okay. Hydrogen. See, atomic number is always written on the left. Atomic number means number of protons, which is equal to number of electrons. So it is only one electron. So what will you write down here? 1s1. Now we go to helium. Helium atomic number is 2. It is 1s2. You can tell me, sir, how do you know? Because we know that first orbit can accommodate up to 2 electrons. Because of that, I have written 1s2. Then comes lithium. See, lithium is 3. So see here, 1s2. Now this cannot accommodate the third electron. So it will go to whom? See, after 1s is what? 2s. 2s. How many are there? Only. Okay. Then comes beryllium. Beryllium is 1s2, 2s. After that comes what? Boron. 1s2, 2s2. You have another electron. So after 2s comes what? See, after 2s is 2p. So 2p. Carbon 6. 1s2, 2s2. So p can accommodate up to 6 electrons. So we write now here 2p2. Then comes nitrogen. 1s2, 2p2, 2p. See, 4 minus 7 is 3. It is. Then comes oxygen, O8. 1s2, 2s2. So 8 minus 4 is 4. And P can accommodate up to 6 electrons. So it will go. Okay. So after that, what you have now? We have fluorine. 9. 1s2, 2s2. So 9 minus 4 is 5. Then comes neon. 10. 1s2, 2s2, and 2p. So 10 minus 4, 6. Yes, p can take maximum 6. 6. Then comes sodium. 11. 1s2, 2s2, 2p6. 6 is 10. Now we have 11. So after 2p comes what? Ps. Ps. All right. So now you will write for, I will not write, you will write it. Okay. So let us go for sulfur. Sulfur is 14. Argon is 8. Oh, you write. I've shown. First you complete it, after that.
So atomic number of sulfur is 16.
Yes, correct. Sorry. I was about to write 16, but I have written by mistake.
Done, sir.
Okay, done. I know, but I want to know for others. Others that don't speak.
Yes, sir. Done, sir.
Others also know, but only two. What about this? There are so many other students are there.
Done, sir, done.
Done, sir.
Okay. Now we'll go for Scandium 21. So Scandium is okay. Before that, I'll go for calcium. Calcium is 20. It is 1s2, 2s2, then 2p610, then 3s2, okay, 3s2, 3p6. All right, 3p6. So how much? 10 plus 8, 18. After 3 becomes what? 4s. So 4s can accommodate. So this is for calcium. Then I'll go for scandium 20. 1s2, 2s2, 2p6, 3s2, 3p6, up to 4s2 is 21. See, after 4s comes what? Not 4p. After 4s is 3d. 3d1. In your book, they have written 3d1, 4s2. Okay, 3d1 in your NCERT textbook, they have written 3d1, 4s2. I have strong reservation. In your school, you can write. But whatever I'm writing, I'm following exactly following the Borsberry rule or N plus L rule, which is not my imagination. This is a scientific truth. Because energy wise, 3D is more than that of 4s, and all atomic orbitals are for energy levels. After scandium is titan, and D can accommodate how many electrons? D can accommodate 10 electrons. Okay, titanium is 22, vanadium 23, and chromium is 20. So please write.
Done, sir.
Done.
Done, sir.
So
Yes, sir.
Done, sir.
chromium you have written. Let
Yes, sir.
everybody write. So chromium you have written as 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d4. Is it not?
Yes, sir. Yes,
Yes,
sir.
sir.
But actually, dear, we have found whatever we have written exactly following the rules, but we find chromium does not follow this electronic configuration. So this is wrong. Chromium does not follow, sorry, I will not write follow here, have this electronic all for chromium, huh? So what is correct electronic configuration? 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, and 3d5. This I'll explain after some time why it is like this. Okay. So after chromium comes manganese. Manganese will follow the same thing. Okay. Then after manganese comes iron. It will also be same. Then cobalt, same. Then comes nickel. This is not going to follow this. This is going to follow the rule. Then comes copper. Copper is going to follow this. So from here to here you write. I write okay. Okay. Copper also you write following the same rule. Then I write the correct one.
Done, sir.
Okay. Now copper. If you write by this way, you get is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. But this is not correct. It is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, sorry, 4s1 and 3d10. Write down. Then I'll tell you the reason. Okay, see what is the reason now? It is found that the half filled and completely filled electronic configuration of element are more stable. See, d orbital has maximum capacity of 10. Half filled is d5. Because of that, chromium, it has borrowed one electron from 4s. It was having 4s to 3d4. It has borrowed one electron from 4s, its nearest orbital, and it has become 4s1 3d5. Same is the case with copper. In this case, it is 4s2 3d9. So 3d has borrowed one electron from 4s and it has become 4s 3d10. But it is going to borrow only one electron, not more than that. So this is the reason for which you got it. Okay. So extra stability of half filled and completely filled orbital is due to right now. One. Okay, first you write, then you tell me, then after that I'll explain and I'll write.
So what is then after electronic configuration of?
Completely, see, it is found that half filled and completely filled electronic configuration of elements are more stable. Extra stability of half filled and completely filled orbitals is due to symmetry. Symmetrical distribution of electrons. Okay, I'll write for, say for, I write for chromium. So I'll write it like this. D orbital. 1, 2, 3. Say it is dxy, dyz, dzx, dx square minus y square and dz square. Okay. It is like this. And this is, I'll write it now here, 4s. See here. What is symmetry? That is in to the middle, if you have passed an axis, if both sides are similar, we call it symmetry. Suppose say you are using a table where you will find one of the leg of the table is small, then you will not be right, you will not be able to write comfortably. Okay, you will feel very uneasy. If one of the leg of your chair is short, when you sit, you will feel very uncomfortable. Sometimes you feel you will fall down. Okay, see here, when this is the middle, if I pass a mirror, left hand side you have 2, right hand side you have 1. So this is 3. So in that case, what will happen? When it will be stable, suppose one of the electron from here, it goes here. What will happen now here? See, here you having, this is having 1 electron, no problem. And if you have this one, 1, 2, 3, 4, so 1 here, 1 here, 1 here, 1 here, and 1. See now, if you pass the mirror, this side also 2, this side also 2. So what is this? This is symmetric. So what you can write here? Symmetry always leads to stability. So half filled and completely filled orbitals are symmetrical and more stable.
Sir, it's not clear.
Written.
Sir, it's not
Symmetry always
clear.
leads to stable. So this, yes. Okay, I'm going to write. Symmetry always leads to stability. So half filled and completely filled orbitals are symmetrical and more. And this is what? This is stable. Do you have class at 5 o'clock? Hello.
No, sir, at 5:30.
No, sir.
Do you have at 5 o'clock?
No, sir.
No, sir.
No, one lady, she was telling something. The electrons, they exchange their position. See, okay, I'll write now here. This is for 3d4. And this is for 3d5. Okay. See here. This is going to exchange its position here, here, and here. This can exchange its position here and here. And this can exchange its position here. So how many exchanges? For this electron, 1, 2, 3. For this electron, 1 and 2. And for this electron, 1. So total is what? 6. 6 exchanges are there. And in this case, see here. 1, 2, 3, 4. Then 1, 2, 3. Then for this. For this, only this. So for first electron, it is 1, 2, 3, 4. For second electron, 1, 2, 3. For third electron, 1, 2. And for fourth electron, 1. So how many this? It is 4 plus 3, 7 plus 2, 9 plus 1, 10. So that makes it more stable. All right. So this is called exchange energy. These are the two factors for which we find half-filled and completely filled orbitals are more stable. So with this, I finish structure of atom. So next we will go to periodic classification.